Okay, so that's the answer you should have there, that the 3.6 nanocoulombs is attracted because the forces are attractive because you've got positive and negative, and it's 5.6 times 10 to the minus 3 newtons to the left. But why is there this force acting on this charge at this particular point? Well, for that we've got electric field. Electric field is the cause behind the effect. The effect is the force, but there's this invisible set of field lines, and the field is defined as being the force per unit charge at that point around a charged object. And you've got the defining equation there equals F over Q, force per unit charge, and so the E is newtons per coulomb, and so force is charge times electric field. So the bigger the field, the bigger the force, and the bigger the charge, the bigger the force that you've got at that point there. So we've got an example here where we've had an electron that was put in an electric field where the arrows of the electric field are going that way, and because it's a negatively charged electron, it will go that direction. So the charge is 1.6 times 10 to the minus 19 coulombs, mass 9.1 times 10 to the minus 31 kilograms, and it's in a field of 230 kilonewtons per coulomb. So you should be able to calculate the force acting on the electron and the resulting acceleration from that. Okay, so if you pause the video just for a moment, work that out, and restart it once you've got your answers. Okay, so let's see what you've got there. 6.7 times 10 to the minus 14 newtons, obviously a very small force, but the acceleration is actually really large. You probably first thought, oh, that can't be right. 4 times 10 to the power 14 meters per second, that would be faster than the speed of light. You're thinking, well, it's not really, because it only accelerates for a very short period of time, and that's because you've got a very small mass. So you can have quite large accelerations in these particle accelerators. A uniform electric field set up between two plates like that, so all the field lines go in order like that, and if you put any positive charge in there, that's the direction it will go. Put any negative charge in there, that's the direction it's going to go. So, and that's the shape that sets up a constant field or a uniform field. More often, we've got a point charge here, and so the electric field lines are always moving from positive either to negative or to 0 volts, which is sometimes taken out as infinity. They always connect with the actual surface of the conductor, so there should always be a contact there, generally at 90 degrees. They will always try and get away from each other, so they'll never cross, and the field lines will always end up at this earth point at 0 volts. And because they're radial away from that point, they should be drawn with a straight line with a ruler if it's a point source. So you've got two charges here, positive and negative, and in which case you can see that the field lines are trying to get away from each other, and that means that they're going off to either 0 volts or to infinity and coming back in, and so they always connect. And so if you added more or other shapes of charges, that's going to change the electric field around there, and the bigger the concentration of field lines, the bigger the charge density is, then you're going to have a stronger electric field. To calculate this, you can actually take Coulomb's law and divide it by any test charge that you put here, small q, so the force between the two would be q1, q2 over r squared. Divide both sides by small q with a test charge here, and you end up with the electric field at that point being establishing charge q divided by 4 pi epsilon naught over r squared, where r squared is the distance from the charge in meters. Bear in mind that these could be nanocoulombs for charge and also millimeters because the distances are quite small. So getting the units correct is one of the first things you need to do. Predicting what that graph would look like if you move away from the charge with the electric field measured in newtons per coulomb, what do you think that would actually look like? Just take a moment, pause the video, sketch it, and see if you're correct. What you should have is something like that. It's going to be a lot deeper than normal hyperbola because it's 1 over r squared and doesn't touch either axis, but it drops away very, very quickly because it is inverse square that you've got there. Because electric field is a vector, It's therefore can be added and subtracted with direction. So if you've got a negative charge here, positive test charge there, it'll have a force due to Q1 which is attractive. Due to Q2, it will be a repulsive force. I'm not sure why this website uses a bigger arrow for F2, because I would expect a smaller force because it's a bigger distance, but let's go with this. So you would add the two together, and so you'll end up with a resultant force just by adding the two together. Here, the two forces are positive and positive, so this charge here will cause force 2 here, this charge here will cause force 1, but because it's closer, it'll be a bigger force, and you'll end up with an overall force in that direction. If you've got the test charge placed out away from the line connecting the two charges, you're going to have a triangle, because that force is in that direction, that attractive force is in that direction towards Q2, so you've got a force vector triangle, and you've got to add those two together as a force vector triangle to give you a resultant, and it's that resultant force. At advanced higher, this angle here will always be generally be 90 degrees, and so that will be 90 degrees, so you can just use normal sine and cosine. If it's different to 90 degrees, you're going to have to use cosine rule and sine rule to work out the resultant in the triangle. And also there's you would need to give the angle relative to the line joining the two centers. Very much an A grade type question, that one. So that's it for electric field and force. At the end of the potential video, there's a short recap and summary. I'm just going to pause there for a moment so you can try tutorial 3 on electric force and field, and then the next video is about potential and energy.